So here we have an object that's being dropped from a 100-foot building. So I'll draw a little person here. They're going to be tossing an object down at an initial speed of 30 feet per second. So it's going down, therefore it's decreasing in height by 30 feet every second, but that's at least the rate at which it exits the person's hand. Because gravity accelerates objects, and therefore dropping your cell phone from let's say a runway of an airport is probably going to cause more damage to your cell phone than dropping it from, let's say, you're sitting in a chair and it falls out of your pocket and hits the ground. So probably going to cause a lot more damage falling from a higher height. And that's because of the fact that gravity actually accelerates an object, makes it speed up. Okay, and so all that goes into this equation, allows us to model the height of the object as a function of time. And at first we wanted to just go ahead and use a table or a graph to approximate after how many seconds the object hits the ground. Well, what I have already ready to go is the equation here. Now, so there's my equation. My window, now x-min and x-max are my minimum time and maximum time. These you might have to tinker around with a little bit to see that between 0 and 2 is enough, but it probably makes sense that an object hits the ground pretty fast from a height of 100 feet. Y-min is 0. I don't want any negative heights because once it hits 0, the object stopped unless it breaks through the ground and continues to the core of the earth. And then Y-max, my greatest height is 100, and so this is the window that I get. So I just want to approximate after how many seconds the object hits the ground. So here's its height, here's the distance as a function of time, and it looks like it hits the ground right there. So a couple of different ways you can do this. You can kind of just drag your cursor over to that point and kind of guess what you think it is. That's going to give us a accurate enough estimate. About 1.36 looks like. Alternatively, if you go to second trace and you select the 0 function, that's for finding horizontal intercepts. You pick a left bound point, you go to the right, finding a right bound point, and as long as these two triangles enclose where that intersection takes place, now hitting enter will have the calculator guess the correct value. So it is, according to our guess, around 1.36 seconds. So x is about 1.36 seconds. If you did it in your table, you could kind of start plugging in some inputs and see that, initially it's at 100 feet, half second later it's at 77, 1 second later it's 38, and after 1.5 seconds it's went through the ground basically. So it has to be between somewhere between 1 and 1.5 seconds. In B, we want to find the derivative of this function. So we will go ahead and utilize our power rule and our constant rule and the fact that we can go term by term. So we bring our 2 down, subtract 1. We have a 1 here, so we bring that down, multiply it out front, subtract 1. Constant becomes 0 because the rate of change of a constant is it doesn't change, no rate of change. And so 2 times negative 32 is negative 64. T to the first power now, because we subtracted 1 in the exponent. 30 times 1 is 30, so I'll have 30 t to the 0. T to the 0 is 1, so I have negative 64t minus 30, and there is my derivative function. We want to determine the speed at which the ball hits the ground. So how quickly is it traveling when it hits the ground? Well, that will be the... Okay, so first of all, we want to know what this function outputs. This is a slope function. This function gives us the slope at any given second. And so on the output, if this is a rate of change, this is going to be change in my output, which is in feet, divided by change in my input, which is in seconds. So this will be, output values that are in feet per second as a function of whatever time I want to determine the speed. So I want to know the speed at 1.36 seconds. So I will plug in 1.36 minus 30, and I believe we get about, I've already done this, nope, maybe not, 1.36 times negative 64 minus 30, and it's traveling at about, we'll say negative 117 feet per second. So it's advancing 117 feet in every given second at that particular moment. In part D, we want to know, well, how fast is this in miles per hour? So we can compare this to maybe the speed of a car. So I have 117 feet in 1 second. So I'm going to use some good old unit conversions here. And I know there are 5,280 feet in a mile, so maybe I'll start with that. So I want to cancel out feet. So I'll have 5,280 feet, and I'm going to go to 1 mile. So feet will go away, and the value that I have will be in miles. So negative 117 divided by 5,280 will be a really nasty small number. I'm going to round this off quite well just to make sure that we get a very accurate answer. So 0.00222159, and this is miles per second. So this should make sense that it's going to be a really small number because this is over how many miles you travel in 1 second. Now this is, of course, traveling downwards because the object is falling. So now we're going to convert seconds to hours, and I'm going to do that in one step because really we're going to need to multiply by 60 twice. First off, I'm going to need to multiply by 60 because there are 60 seconds in 1 minute, and that will get me into minutes. So I'll have miles per minute, but then I want to go from minutes to hours, and I know there are 60 minutes in 1 hour. So I'll basically have to multiply this by 60 2 times, and I will be in miles per hour. So I'm going to multiply by 60, and I'm going to multiply that by 60, and so I get around negative 80 miles per hour. Wow, okay, so this object is traveling downwards at negative 80 miles per hour. That's what it would be clocked at as it hits the ground. So this is faster than a speeding car on the freeway. So imagine any object that's solid, like a rock or, gosh, even a ball of some sort, could really cause some pain to somebody as it crashes down on them, assuming they're right at ground level. And in part E, we want to know what type of moving object. So yeah, we said faster than a speeding car on a freeway.